Welcome to this lesson on the geometry of vector spaces. Let's dive right in and introduce a new concept. This is called the dot product. And here's how the dot product's defined. If you have some vectors, this one is A, B, C, and so on, and this one is D, E, F, and so on, then the dot product of them is defined as, well, you multiply the first element, so that's A times D, and then you add it to what you get when you multiply the second element, that's B times E, and then you just keep going, plus C times F, and so on. So to get kind of specific about this, if we do this example, 1, 3, dotted with 2, minus 2, the answer is 1 times 2, plus 3 times minus 2, that's 2 minus 6, which is negative 4. All right, that's the dot product. Now here's how we use it to do something geometric. One of the things we can do about this is talk about the length of a vector. So let's consider the vector 3, 4. Okay, so that's this vector, 3 over 4 up. Okay, and we would like to know how long that vector is, and you say, oh, I took geometry, so I know that I can kind of think about a right triangle, and since this up here is the point 3, 4, that means that this side has length 3, this side has length 4, and so this side has length square root of 3 squared plus 4 squared. Okay, well, we can get that same result using a dot product. So if we take this vector, we notice that if we dot it with itself, what we get is 3 times 3 plus 4 times 4, which is 3 squared plus 4 squared. The length of the vector is the square root of that. So in general, for a vector u, and this is notation for a vector, if we're talking about just a vector that has a name, we'll sometimes put that name in boldface or sometimes put a little hat over it to represent vector. If we have a vector u and we want to know the length of u, and you sometimes see that denoted by single or even sometimes double bars. Okay, that means length of. The answer is that you take that vector, you take the dot product with itself, and you take the square root, right? So for our example, for 3, 4, you would dot 3, 4 with itself. 3, 4, dot 3, 4. That's equal to 3 squared plus 4 squared. But then we're not just supposed to dot it with itself, we're supposed to take a square root. So you take the square root of 9 plus 16 is 5, so that vector has length 5. Okay, so this is how you can find the length of a vector using the dot product. And that'll be useful to us later in this unit. That's not the only thing that you can do with the dot product. You can also determine if vectors are perpendicular, and another word for perpendicularity is orthogonality. Okay, so this means perpendicularity. And the thing to know is that if you have two vectors u and v, their dot product equals 0 if and only if they're perpendicular. Okay? So it goes both ways. Like if you have two vectors and you take their dot product and it's 0, it means they're perpendicular. If you have two vectors that are perpendicular, it means that their dot product must be 0. So to give you an example of this, let's take the vectors 1, 2, and 1, 1. Okay, and let's take the dot product of them. It's 1 times 1 plus 2 times 1 equals 3. 3 is not equal to 0, so these vectors aren't perpendicular. And we can see that by drawing, right? 1, 2 is this vector here. 1, 1 is this vector here. Definitely not perpendicular. Okay, but let's do another example. Let's do 1, 2, and the vector 4 minus 2. Well, that's 1 times 4 plus 2 times minus 2. That's 4 minus 4 is 0. So these are perpendicular. And 1, 2 is this vector. Let's plot 4 minus 2. That's this vector. So this angle here is a right angle. Okay, this also works in higher dimensions, right? So as another example, if we have the vector 1, 3, 7, and we have the vector 2, 4, minus 2, and we want to know if they're perpendicular. We can take the dot product. It's equal to 1 times 2 plus 3 times 4 plus 7 times minus 2. That's 2 plus 12 minus 14, which is 0. So they're perpendicular. Since these vectors have 3 elements, you should think of them as living in a 3-dimensional world. And you can picture what perpendicularity looks like in a 3-dimensional world. Even if you had vectors that had more than 3 elements, so you could not visualize them easily in your head, you could have a vector that has 20 elements and ask if it's perpendicular to another vector that has 20 elements. The dot product is what tells you what to do. Let's introduce a new concept, span. What span means is that the span of a set of vectors that I give you is just all of the linear combinations of all those vectors. And since you have now learned that a way to think about linear combination is as sort of like following directions around, taking certain numbers of steps of different vectors to try to reach different locations, the span of a set of vectors is just all of the different places you can get to using those vectors, right? So if I ask you, what is the span of 1, 1, right? You think of the vector 1, 1, and you think, what are all the places I can get using that vector? Well, you can get along here, so it's a line, okay? You could ask, what is the span of 1, 1, and minus 1, 1? Okay, so it's the same vector as before, but now you can also take steps in this direction, and you should be able to convince yourself that the span of these things, while this first one was a line, the second one is the whole plane. If you have this vector and this vector, you can actually reach any location. It's kind of like saying, if you're walking in a big field and you're allowed to walk, in this sort of northeast southwest direction and in this northwest southeast direction, can you get anywhere? And the answer is yes. Okay, these ideas work though in just more than 2 dimensions too. So we can ask, what's the span of the vector 1, 1, 1? Well, that has 3 elements in it, so you should picture a 3-dimensional world. Here's a 3-dimensional world, and I don't know, I'll just draw a vector in that. And even though you're in a 3-dimensional world, all you can do is travel along the direction of that vector. That still defines a line. So the span of this single vector is a line. Okay, we could talk about situations where there's even more than 3 elements. So these are situations that you won't be able to visualize in your head. But we could talk about 1, 2, 0, 0, and 1, minus 2, 0, 0. And we could ask, what's the span? Okay, and well, you can see that by taking linear combinations of these 2 vectors, no matter what linear combination you take, the bottom 2 vectors will always, or the bottom 2 elements will always be 0. So really what you'll be able to get to is locations that have any value in the first element and any value in the second element. That's basically a plane. It's like you get to choose an x value and you get to choose a y value. So the span of these things would be a plane. Now at this point, you're doing hard mathematics. I'm asking you to envision a plane somehow like embedded in a 4-dimensional space. Space has 4 dimensions here because 4 elements in these vectors. You can't really picture that in your head, but this is basically what we're doing. The only other thing I want to say about span, to connect it to the talk we've been doing about linear equations, is that when you write something like a linear combination, like x 210 plus y 110 equals 625, what you're asking is, are there any steps you can take of these 2 vectors to get to this vector? And in the current language, this means, is this vector on the right-hand side in the span of these 2 vectors? Okay, in this case, it turns out that it's not. But this is useful language because when we want to talk about whether or not linear equations like this have a solution, what we're really asking is the right-hand side target vector in the span of the other vectors? Now let's introduce the concept of linear dependence and linear independence. The definition is that a set of vectors is linearly independent if no vector in the list can be written as a linear combination of the others. Or to say it the other way, if a vector can be written as a linear combination of the other vectors in the set, then the vectors are linearly dependent. Okay, so let's do some examples. Okay, suppose I give you 1, 1, and 1, 2. And I ask you, are these linearly dependent or independent? The answer is independent, because there's no number there's no linear combination of this single vector you can take to get this vector, right? I can't multiply this by anything to get this one, right? So this is linearly independent. Okay, here's another example. Say I take 1, 1, and -3, -3. Well, these are linearly dependent, because if I take the first vector and multiply it by -3, I get the second vector. And if any vector is linearly dependent to the others, then the others are linearly dependent to the one. It always goes both ways, right? I could start with the vector -3, 3, say I multiply it by -1/3, and I get this vector. Let's do another example. Let's start with these two original vectors, 1, 1, and 1, 2, and I'm going to add a third vector on. I'm going to add, let me think about this for a second, 3, 4. And I'm going to ask if these are linearly independent or dependent. I claim they're dependent, so I claim that I can pick any two of these three vectors, I'll pick the first two, and take a linear combination of them. There's a linear combination, and get the third vector. And is there a solution that does this? Well, I can see what the solution is by inspection, but if you can't see it, just write out the equations. Read across the top row, you get x plus y equals 3. Read across the bottom row, you get x plus 2y equals 4. I'm going to subtract. I find minus y is -1, so y is equal to 1. Plugging in back here, if y is 1, then x equals 2. So I showed that this third one can be written as a linear combination of the first two, so these are linearly dependent. To put it in other language, we can use this notion of span. We know that these first two vectors are linearly independent. We said that up here. We also can ask what their span is. Well, their span is the entire Cartesian plane, the xy plane. Okay, so you can use these two to get anywhere in the plane. This third vector is just a location in that plane. Adding it into this first list doesn't let you get anywhere new. You can still just get everywhere you could originally get, okay? So another way we think of linear dependence is redundancy. Like you add another vector into the list, does it let you get somewhere that you couldn't get before? Here the answer is no, so they're linearly dependent. Do another example, and let's get above 2 dimensions. Let's at least go up to 3 dimensions. Say I have the vectors 1, 1, 1, 3, -2, -1, and 5, 0, 1. I'll call these U, V, and W. Well, we can start with U and ask if adding V into the list makes it linearly dependent or independent. Since V is not a scalar multiple of U, we know that at least U and V are linearly independent. Now we can ask if adding W in makes it linearly dependent or independent. And my claim is that W, this vector W, can be written as a linear combination of the other two. It's actually 2U plus V. If you don't believe me, you can pause the recording and actually do the calculation yourself. Just do the multiplication and addition. So since W is can be written as a linear combination of these are linearly dependent, okay? And then we can also ask, well, what is the span of these? So the world here is 3-dimensional, since each vector has 3 entries in it. 2 linearly independent vectors in a 3-dimensional space, or in any space, span a plane. So since we have 2 linearly independent vectors, we have a plane. Okay, we have 3 vectors, but they're redundant, so it's just any two of them are linearly independent. That gives you a plane as the span. We could also say what the span of these things are. We kind of said it, but let's be explicit. Here we're in 2 dimensions, 2 linearly independent vectors. We have a plane. Here, these are linearly dependent. So you just have one vector in the plane. That gives you a line. This is the same as the first one, same span. This third vector was redundant, so we had a plane here. This is just to make explicit and more concrete something we've sort of already been saying, which is to talk about the dimension of what is spanned by some vectors, right? So if I have the vector 1, 1, we said the span is a line, and that is a line is a one-dimensional object. Okay, if we have the vectors 1, 1, and 1, 2, these are linearly independent. The span is a plane. This is a 2D object. In general, n linearly independent vectors, you get those span an n-dimensional object. Like if you had 3, it would be 3D space. If you had 4, it would be 4D space, which is hard for us to envision in our heads, but that's okay. And knowing that kind of helps you understand this idea of linear dependence or independence, right? So like say we lived in a 5-dimensional world. So I had the vectors 1, 2, 0, 0, 0, and the vectors the vector -2, -4, 0, 0, 0. Okay, well, even though I'm in a 5-dimensional world, I look at these two vectors, I see that they're linearly dependent. The second one is -2 times the first. So I have one linearly independent vector. So the span of these things is a one-dimensional object. It's a line, right? If I had, I can even write that down. The span is a line, which is 1D. If I had 1, 2, 0, 0, 0, and 1, 2, 4, 3, 7, the world is still 5-dimensional because there's 5 entries in the vector. I can see that the second one is not a scalar multiple of the first, so these are linearly independent. I have 2 linearly independent vectors. They span a 2D object. That's a plane. So the span is some plane in a 5-dimensional world, but that plane is still a 2D object. Let's revisit linear equations. Just for the sake of concreteness, suppose I give you vectors u, v, w. I'm just picking 3, but there's nothing special about having 3 vectors. And suppose we'd like to solve xu plus yv plus zw equals b. In other words, b is the vector we're trying to get to. We're asking if there are multiples x, y, and z we can take of u, v, and w in linear combination to get to our target vector. You might remember from previous screencasts that there can be 0, 1, or infinite number of solutions, and we want to now try to understand this in the language of span and linear independence. So the first thing is that if b is not in the span of the vectors I give you, you simply can't get there. That's what span means. So if b is not in the span of u, v, w, there's 0 solutions. Now, if b is in the span of u, v, w, and if u, v, w aren't redundant, in other words, if they're linearly independent, that means there's going to be one solution. There's going to be exactly one way to get to your target. On the other hand, if b is in the span of those vectors, but those vectors are redundant, meaning they're linearly dependent, well then you're going to have lots of different ways you can get to b. That means there's going to be an infinite number of solutions. Let's do some quick examples. Here's one set of linear equations, x 1, 0, minus 1 plus y 1, 0, 3 equals the target 1, 1, 1. We ask first, is the target in the span of the vectors we were given? The answer is no, actually, because no matter how many combinations of these two vectors we take, the middle entries here is always 0, so you're never going to be able to create a 1. So this is not in the span of these two vectors, and therefore there are 0 solutions. Next example, x times 1, 0, minus 1 plus y times 1, 0, 3, so the same left-hand side, equals a new target, 3, 0, 5. So in this case, we ask, is the target vector in the span of these two vectors? And the answer is definitely yes. I can come up with an example. The example is x equals 1, y equals 2. One step of this guy, 2 steps of this guy, I get here. Okay, so I know that it's in the span. Now I check these two vectors to see if they're linearly dependent or independent. Well, one is definitely not a scalar multiple of the other, so they're definitely linearly independent. When the target's in the span and the vectors you're given are linearly independent, there's exactly one solution, and indeed, it's the solution that I wrote down here. All right, here I have x, 1, 0, minus 1, plus y, minus 2, 0, 2, equals 4, 0, minus 4. First question is the target in the span? And I say, sure, I can find one answer, x equals 4, y equals 0. So there's a solution. So there's at least one solution. Then we look at the vectors we're given and ask if they're linearly dependent or linearly independent. Well, the answer is dependent, because I take the first one, I multiply it by minus 2, and I get this one. That means there's redundancy in those vectors. There's many different ways, an infinite number of ways, in fact, for me to get to the target vector. We'll write down just a couple. I could take x equals 0 and y equals minus 2. I could take x equals 2 and y equals minus 1, and I could keep going on like this forever. Here, there's an infinite number of solutions. Yourself if you can do the following. Can you compute a dot product, find the length of a vector, determine if two given vectors are orthogonal, describe and determine the span of a set of vectors, define and determine the linear independence if certain vectors are linearly independent or linear dependent, and then discuss the number of solutions that a set of linear equations has using these concepts. Thanks for listening.